This is chapter 15 in your text, talking about milliampere seconds, or mAs, mass. So some reminders here. Some of you have had this. This is sort of like a review chapter. It's specific to mass. We've talked about mass in different contexts before. So let's start with what it means electrically. Inside the equipment, using electricity to produce X-rays, you need to send some electrons across a gap in space, and you smash them into some target, right? We talked about that process. But just very simply, if you're talking about electricity in general, not necessarily in the X-ray tube, amperage is a number telling you how much electricity is flowing through a wire, okay? Milliamperage is that same thing. It's just a smaller number. Milli is the prefix meaning 1/1000th of something, okay? So if I have an amp flowing through a wire, that's a number, 6.3 times 10 to the 18 electrons moving past a point every second. If I have 1 milliamp, 1/1000th of that, then I have 6.3 times 10 to the 15th electrons moving past that point in 1 second. So we can quantify exactly what we mean when we say a milliamp. We could say it's this many electrons, okay? Those numbers were accurate numbers, by the way. 6.3 times 10 to the 15 is that much electrons. 6.3, 15 zeros, or move the decimal point 15 places. Okay, to the right. Radiographically, at the control console, MA controls, is selected, is set from a series of resistors. And if you remember Ohm's law, voltage equals amperage times resistance, you remember that resistance can affect amperage. Okay, so real quickly, we're not going to do any equations with this, but ignore everything above this, but Ohm's law, voltage equals amperage times resistance. If you fix this number, voltage, if it can't change, then if resistance goes up, amperage must go down, okay? And if resistance goes down, amperage must go up, okay? There's an inverse relationship. So in the X-ray room, let's go over to the control console. When you switch between 50 mA and 100 mA, you're raising the amperage, right? So you are lowering the resistance in the wire that's controlling this stuff, okay? Cutting the resistance in half, the voltage is fixed, so cutting the resistance in half doubles the amperage. Going from 50 mA to 100 mA is a doubling of the amperage, so we have to cut in half the resistance. These resistors are little electrical devices that when you decide to go through them, the path through them, you will have a different amount of electrical resistance than the one next to it, okay? And your MA control just plugs you into one of several different resistors in your electrical component to change the resistance in the wire, thereby changing the milliamperage flowing through the wire, the MA number, okay? It's all based on that, voltage equals amperage times resistance, Ohm's law. So, milliamperage. High amperage current flows through a thin filament in an X-ray tube, the cathode, if you remember those terms, causing friction in the cathode and ejecting the electrons into the space around the cathode. It's similar to when an incandescent filament light bulb lights up, okay? Similar, but a little different. Instead of light being emitted, which does get emitted, we're causing the electrons to hop off of the wire that they're flowing on, okay? We say the electrons are liberated, creating what's called a space charge, a little cloud of electrons, a little charged cloud of electrons around the filament, which as long as you are pressing the rotor button, you know if you've been in the X-ray rooms at all, there's two buttons, right? Prep and expose. The prep button spins the rotor, right? And on the other side, the cathode side, it builds a charge in the filament, okay? You notice that if you've done this, you have to wait, right? It doesn't happen immediately. Some newer systems are very quick. You press the prep and immediately it's up to speed and ready to expose. But most of the time, like here, you have to prep 1-2 seconds and you hear a beep or a click, right? some light comes on a different piece of equipment, and you know that it's ready to make the exposure now. It took time to spin the rotor up to speed and to build the charge on the cathode side of the X-ray tube, okay? So both of those things happen when you hold the prep button down, the rotor button, which is one reason why we want to minimize the amount of time that we're rotoring. If you work with children, who's ever taken a chest X-ray on a small child? A couple of us, right? Any experience with that? Like, how old was the kid and how'd it go?
4 and they couldn't stay still.
Yeah, couldn't stay still, right? Usually they like throw their heads around, or you tell them to hold still and they go, what? You know, and they walk away, right? How did? Do you mind sharing anything about how you got through it?
We bribed him with a lollipop.
Bribed him to stay still with a lollipop, and were they able to follow breathing instructions? Hold your breath, take a breath in, and hold it.
Yeah.
Okay.
Well, his mom told him, and he listened to his mom.
Good. Parent help is useful. How about you?
With a baby, so the mom held it.
How old was the baby?
It's a baby.
A baby, right?
Baby.
Less than a year infant?
Infant.
Now, is the infant going to follow breathing instructions?
No.
So what did you do? You
prayed.
have the mom hold the baby, right? Dad or mom hold the baby, right? You prep, and then we have to take chest x-rays on a lung full of air, right? So what do? We wait for them to take a breath in. That means we have to be ready to make the exposure when they take a breath in, which means we have to prep and hold that button down and wait for them to take a breath, which is sometimes difficult to see, right? So we have a device called a pigastat in x-rays, in the x-ray room. If some of you have heard of it, it's this medieval looking device that's basically, at its core, it's just a plastic tube that we stuff infants into, okay? And holds their arms over their head like this, and guess what? It pisses them off. It's cold, it's uncomfortable, and they get really upset, but guess what? They can't move, okay? They can breathe because their arms are above their heads, so they can breathe like that, their lungs expand. So what do? They cry, okay? And they cry and they cry and they cry. Well, what's crying? Crying is an exhale, okay? At the end of a cry, the baby has to go like that, okay? So you just sit there and you wait. You let them cry. They can't go anywhere, so they cry and you prep. They cry it out and they go right at the end of that cry. They inhale and you prep, you expose immediately at the end of their inhale, okay? It means you have to time it right, yeah? The whole time you're building a space charge, you're using the equipment's usable life the whole time you're doing that. Those are times when you have to excessively prep you have to sit there and let it stay ready, right? Most of the other time, you don't. Most of the other time, you, go ahead. Most of the other time, you just, make the exposure. You have the patient hold still and then you make the exposure, yeah? There are times when we need to excessively rotor. It's always a good, important note to mention that these machines have a usable life, and everything you do to them is using them, right? So you're taking away from their usable life. It's not infinite. MA gives us, that was a long digression. Anyways, it's useful for time talks to the seconds exposure time. MA gives us beam intensity. Okay, it tells us what our intensity rate of the X-ray beam will be. Said in a more simple way, it tells us how many X-rays will be in our beam. Okay, now you're not going to, in principle, calculate that because you don't know. For a single electron going from cathode to anode, you don't know how many X-ray photons it's going to make, right? If every one of them made one X-ray photon, then you could maybe calculate that a little bit accurately. But you can't really, because one electron can make many X-ray photons, or it can make one, or it can make none, right? It depends, right? Remember the characteristic and Brem's interactions in the anode, right? It's sort of hard to tell how many interactions are going to happen, yeah? You can say for a given interaction what the energy will be, but you don't know how many interactions there's going to be. So you don't know how many X-rays will be in the beam. What you can know is, the lesson is, if you double the milliamperage, you know you're going to make twice as many X-rays. So you can know a relative number. You can say for a given MA, I make X amount of X-rays. Double that MA, I make 2X amount of X-rays, twice the number of X-rays. The other factor in intensity, or the number of X-rays in the beam, is time, little s. Okay, big S got taken by the concept entropy in physics, so we use a little s for seconds. The number of seconds during which an exposure is occurring is time, and all you do is take the milliamperage setting, multiply it by the time setting. Okay, usually usually you know what your mass is. Okay, usually you know what mass I'm supposed to use. So then it's a question of what combination of milliamperage and time do I actually set to get that mass number? It's an electrical factor, milliamperage and time, right? Exposure, time, and milliamperage. But what it controls is, it controls the exposure. It directly affects the exposure to the patient, okay? Doubling the milliamperage or doubling the mAs will double the patient's X-ray exposure. Because what are you doing? You're doubling the number of X-rays in the beam. Notice none of this has anything to say about beam energy, the energy of the beam, the penetrating power. It's just saying how many X-rays there are. That's MAS. Mass, MA, and time are directly proportional to exposure. Someone break that down for me. What does that mean if something's directly proportional to something else?
Related.
They're related, right? So let's say mass goes up. What happens to exposure? Let's say you double mass. Doubles the exposure, right? Notice it's not double mass equals 4 times the exposure, right? That would be an exponential relationship. It would follow some exponent power law type thing. It's direct and proportional. So direct means if one thing goes up, mass, the other thing goes up, exposure, right? Inverse would mean if one goes up, the other goes down, okay? Like we talked about with Ohm's law, okay? It's direct and proportional. Could not be an easier concept. You double one thing, the other thing doubles, okay? Mass is the primary factor for X-ray exposure. How many X-rays are in the beam controls exposure. Mass is the controlling factor for that. Because mass does not affect the penetration of the beam, that's governed by beam energy. So here's an example. These are film radiographs done at, everything is fixed. SID, OID, focal spot size, KVP, everything has been fixed. All that they've done from one image to the next is change the mass. If you did experiment lab number 1 with me, this is one of the experiments in lab number 1. You take something and you fix everything else and you change mass through different images, okay? So this image, first one, was done at 10 mass. It's kind of bright, yeah? So visibility is low. As you double the mass, notice the image gets a little bit darker, a little bit more dense. Brightness goes down. Double the mass again, the image is darker, more radiographically dense, even less bright, and we get, if you look from 1 to 2, if you kind of zoom in on them, 20 mass to 40 mass, I get more detail. Like I can see more of the carpal bones here. Notice the carpal bones are now more visible, yeah, because they've changed brightness. So notice, didn't change the shape of anything. Recognizability has not changed. This and that are just as recognizable, but now they're more visible in this one. Okay, I can see carpal bones now where I couldn't see them before. So adding mass gave me more visibility, more structural visibility. Okay, but notice what happens when you add too much mass, right? Too much mass, so 40 to 80 mass, I've now lost visibility because of oversaturation. The image has too many X-rays getting to the receptor, and the receptor gets blacked out in a lot of areas, overexposed in a lot of areas. Now I've lost visibility of those fingers. Okay, so visibility is affected here. And also, at this extreme end, recognizability is also affected, right? I can't recognize the fingers if they're not visible, right? Something has to be visible to be recognizable. So at extreme ends, mass affects recognizability, not by changing the shape or size of anything, which is typically what we think of as recognizability, but by just not making it visible to you, because it's blacked out. We had to go from 10 mass all the way to 80 mass. So 10 mass was sufficiently underexposed to say we have loss of visibility due to too much brightness, 10 mass. And 80 mass was a loss of visibility due to not enough brightness, too much density. Brightness and density are opposites of each other. Okay, yeah.
I think there should be like an in-between between the 20 and the 40.
Sure.
Maybe like 35.
Sure.
Because they both...
Sort of optimum.
Yeah, they both still fuzzy.
Yeah.
But 20, it's like the tips are too bright and then
right.
they're too dark.
So none of these are ideal,
no.
right? All it's showing you is that they how it changes, right? So yeah, if you wanted to go what's ideal, none of these are ideal, right? Maybe somewhere between 20 and 40, you'd find that happy spot. And notice we haven't changed KV. If we added KV into the equation, we could probably get a nice, good, visible image down at the lower mass numbers with higher KV. That's the next talk. All right, next concept to get out is underexposure and how that relates to this idea called model or quantum model. Quantum model makes it sound cooler than it is. It's not.
It sounds more.
Makes it sound smarter, right? It's quantum, so it must be cool. All right, so think about the X-ray beam like a shower of X-rays, okay? I gave an example, an analogy last time of raindrops on the sidewalk, right? When there's a dry sidewalk, no rain, there's no exposure to the sidewalk to rain, right? The sidewalk has not been exposed to rain. As the rain starts, a very light rain, you would notice drip, drip, drip drops on the sidewalk, right? And spaces between those drops. So the drop would represent a spot where the rain hit the sidewalk, and the spaces between that would represent spaces where no rain hit the sidewalk, okay? We would say that had a granular or grainy appearance to it, right? You see drip, drop, drop. You can tell each individual drop, okay? But as the rain increases, or just goes for longer, right? Either more rain, milliamperage, or longer rain, time, right? Either one can do it, right? A little bit of rain for a long time will saturate the sidewalk. And a lot of rain, if it just pours down immediately, right, for a very short amount of time, that also saturates the sidewalk, right? So you see how milliamperage and time both affect the same thing. But given time or more rain, the sidewalk gets completely saturated. Now you can't tell where individual raindrops are. It's fully saturated, okay? The point where it gets to where you get the sidewalk looking grainy, where you see each individual drop, is like underexposure on an X-ray. Okay, on the X-ray, the X-rays make tiny little dark spots. Okay, on the X-ray image makes tiny little dark spots. When you don't use enough of the X-ray beam, enough mAs mass, you will have spaces between those X-ray exposure spots on the image receptor, dry spots on the sidewalk, and you can see those dry spots like you can see them on the sidewalk, okay? And the image appears grainy to you. It's underexposed. It is bright to begin with because it's underexposed, but then it's also got this granular or grainy appearance to it. When you see this grainy appearance, we call it model or quantum model, and it's due to an insufficient amount of X-rays reaching the image receptor. This can come from insufficient mAs, or it can come from insufficient KVP, which we'll talk about later. So you want to ensure adequate exposure to the image receptor. Said in another way, we want good signal, right? We want enough signal reaching the image receptor. Good signal.
We get a lot of these with drip.
A lot of model?
Yeah.
Yeah, because either insufficient KV or insufficient mAs, right? So you take the body thickness, right, and you calculate some mAs for it. Remember the 4 centimeter rule for mass? What's the 4 centimeter rule say?
For every 4 centimeters, you double the mass.
Yeah. So a body part's 4 centimeters thick and takes 10 mass. Another person comes in with an 8 centimeter same body part. Go to 20 mass, right? Double it. Okay, for every 4 centimeters, double your mAs, because the tissue that you're going through absorbs the X-ray beam, and every 4 centimeters of tissue absorbs 50% of the X-ray beam. So if you add another 4 centimeters, it's going to absorb half of the beam, so double the amount of that's in the beam. Okay, it is. Go ahead. KVP follows the 15% rule, which we'll definitely do that. Yeah. Here's a real world example. This was done under fluoroscopy, and all they did was take some tissue equivalent thing and put catheters in it, 3 catheters, okay? In image A, with insufficient MAS, it's mottled. Okay, it's granular, grainy, right? It's hard to tell where those 3 catheters are. I can see 2 of them, yeah, the top one and the middle one, those dark spots, those dark lines, right? So there and there, right? I can see there's something going on there, right? As you add MAS, or in fluoroscopy, we don't say MAS, we just say MA, because fluoroscopy is like a video where it's not a single exposure, right? It's many exposures, right? So we just let the machine play, right? We just turn on and it's like a video. So we say MA, right? So MA would be doubled, let's say, from A to B. I don't know if it was actually doubled, but let's say that. MA gets doubled, more x-rays hitting the detector now, less grainy. Now I got, okay, there's a thing there, and another one there, and now I can kind of start to make out that there's something going on down here too, okay? Becoming less grainy, increasingly visible. And then we get to image C, let's say we double the MA again, I now see a nice clearer dark line representing the catheter, another line representing this thinner catheter, and now I can start to make out better that there is a 3rd catheter on the screen or on that image. It's more visible on my screen, I bet it's even more visible in the textbook. The point remains, though, that model becomes less visible as you increase MA or time or both, right? There's a point where you add too much intensity to the beam, and now it's overly exposed and overly dense, but we're talking about the underexposed side of it, right? So you're trying to achieve optimum exposure. If you use too little, you will make the image too bright and mottled. If you use too much, we get overly dense, dark, okay? That was represented by those hand x-rays you saw a second ago.